On previous lessons, we calculated the electric field of district charges. All right, so if you have maybe 4 district charges which are in space, and you point or you just put a test charge between those charges, you can be able to calculate the electric field strength due to those district charges. All right, but now for the purpose of this video, what I want to do, I want to show you on how to calculate an electric field strength when you have continuous charges. All right, for instance, you have this rod here. All right, so you have this rod. Let me draw a rod. So you have this rod. So this is a rod. All right, so you have this rod, and we decide to charge this rod. All right, so when we charge this rod, maybe we wrap this rod or on something, right? We wrap this rod to a cloth, right? As we wrap this cloth with this rod, which means we will have a line segment of charges, right? Line segment of charges, infinite number of charges, right? We will have infinite number of charges that you can see from this rod. Let's say this rod is placed along the x-axis. Let us say this is along the x-axis. Let us say this is along the x-axis. All right. So we have this infinite number of charges, which means we have a continuous charge distribution. What does that mean? It means we have infinite number of charges, right, sitting on the surface of this rod after charging this rod, right? But now we have this question whereby we need to determine the strength of an electric field. Let us say we want to determine the strength of an electric field, maybe in this position, all right? In this position, or in the origin, all right? Let's say we put in the test charge, right? So we put in the test charge here. Remember, I said, right, you can be able to identify, we can be able to calculate the strength of an electric field at any given geometry by using a test charge, right? So we assume that the test charge is positively charged, right? That's what we're assuming, right? So we can't use a test charge that is negatively charged, right? So now what is happening to this situation, right? We said that this charge is placed along the origin, or is placed at the origin, which means in two dimension. In two dimension, what we'll have y here, and here we have x, right? So this is along the negative y-axis, right? So what is the question again? So the question again will be like, we need to determine what? We need to determine the electric field strength, because as we have this positive charge, which means you produce what? You produce some electric fields, right? Each and every charge in this rod will produce its own electric field. And when you sum that electric field, that can give you the net electric field, right, of this rod, which is charged, right? So let's say I put this just charge here, right? Or put this just charge here, which is Q0. We put a test charge here at 0 or at the origin, right? So how do we calculate the electric field strength at this position, right? Remember, the first thing I said we need to do, we need to identify the direction of an electric field, because the electric field is what? Is a vector quantity, right? So what is the direction of an electric field in this situation? Right. So how do you imagine it? You imagine it in the situation whereby you relate the electric field with what? With force. Right. You remember the force is what? Is there's a relationship between force and electric field. All right. So now when you have that relation in mind, you can simply say, oh, that means the electric field for this situation is going in that direction. Why we have the electric field going in that direction? It's because of this positive charge, which means they are repelling each other. That's why we have the direction of electric field pointing toward that direction, right? So that one is very important to know. So which means here we'll have the electric field, right? So this is an electric field along the x-axis. Remember the unit vector. The unit vectors are along the x-axis. You say the unit vector along the x-axis here is I. and here is it's j, right? These are the unit vectors indicating the direction. And what about here? Here, because it's negative y-axis, which means here we'll have negative j, and that side we'll have what? We will have negative I, right? The side of the Cartesian plane. Correct, yes, Cartesian plane, right? So now we have this situation here. We have this rod which is linearly charged, right? So now we are told to calculate the electric field strength at this point here, right? We place the test charge at the origin, which is 0 map 0. So how do we calculate the electric field in that type of situation? Remember, the electric field is defined to be electric field is equal to 1 over 4 pi epsilon 0. All right. So integral line, because this is line charged, right? dq over r squared r unit vector. All right. So now let us define each parameter, each and every parameter present in this equation. So this is from definition. So from definition, we can simply calculate an electric field due to continuous distribution of charges, right? So they are continuously distributed. They are no longer discrete charges, but they are continuous, which means we have infinite number of charges on the surface of this rod. All right. So now, what is this dq? All right. So we can simply find dq by selecting any region. For instance, let's say we selected this region here, the small region. All right, small region here, and we can simply say that region is dq, right? That region is let's say dx, right? Because the small segment of this x along this x-axis, we are selecting this small segment, right? So this is dx. Within this dx, if you can zoom in this dx, right? So this is our dx, right? So what we are doing here, we are zooming this dx, right? So as we are zooming this dx, which means in this dx, right, we will have not only one charge, but we have a density of charges, right? A density of charges, which means there are more charges which are dense within the selected region, right? So how can we calculate that? How can we find the dense charged to the selected area? All right. So since these charges are distributed linearly, which means we can use the linear charge density, right? So how can we use the linear charge density? You remember, we said the linear charge density is defined to be what? To be dq over what? Over L. Right? Now let me write the proper, let's say it's Q over L. So what is Q over L, which is a linear charge density, which means the total charge of this rod can be determined or can be simply defined to be what? To be lambda times L, because we can simply say the length of this rod is of length L, right? So it's of length L. It's of length L, right? But now, since this is a total charge, right, of this rod, but we are not interested for now in the total charge. We are interested in the number of charges which are present here, which means we want to find exactly our dq, right? So using these two quantities, which means we can represent what? We can represent dq in terms of dx, because the length of this selected region, right? You see, this selected region, the length of this selected region is dx. Right, so how do we find the linear charge density of this selected region? Right, so we can simply say in that particular case, we can express this dq in terms of a linear charge density, which means this dq can be written as what? As lambda times dx, right? So for this situation here, but for this situation here, which is a total rod, we can represent the total charge of this rod using this quantity here, which is a lambda times L. So this is the total charge. For this case, whereby we are selecting a small region, which means we need to say dq is equal to lambda times dx, because dx is the total length of that selected region. All right, which means from this equation here, we know exactly what is dq, right? We know exactly what is dq. All right, so now we can simply say the distance between the test charge and this dq, we can denote it to be what? To be x. So the distance between the selected region and the test charge is x. All right. Right, which is very easy, right? Why we need this distance? We need this distance because we have to express that r squared. Remember, r squared is a distance between q1 and q2 in discrete charges. But in this situation, we have dq and q0, right? So what is the distance between q0 and dq? So we denote it by x. Another important aspect that we can learn from here is that what is the distance from here to here, which is from our test charge to this to the tip of this rod. We can simply say here it's A, right? So we can simply say here it's A, all right? Okay, so what else that we need to know? What else that we need to know? All right. So from this equation here, let us write everything down. All right. From this equation here, from definition, our dq, right? So we already know how to find this dq. It's lambda dx, right? What is our r? Our r is x, right? Our r is x, right? So now, what about this r here, which is the r unit vector, right? So that one is very, very important to know. That from definition, we can define the unit vector to be r vector over r magnitude, right? So how do we do it? So in this particular case, we can simply say, what is r vector? Right, what is r vector? So the r vector is the distance between the test charge and the selected region, in this case, which is x, right? Is x in which unit vector? Along the I unit vector, which means we have x over I divided by, right, divided by the magnitude of x. So what is the magnitude of x? The magnitude of x is gonna be x again. All right, I'll show you shortly why it's x, which means r unit vector is gonna be I, right? So which means the direction of an electric field, right? So now, what is happening here? Which means from here, what we can have this situation, right? I wanted to show you how do I obtain this x, which is the magnitude. So if we have a, right, is an absolute a, which means we have the square root of a squared, right, which is a squared times 1 over 2, which is equal to a, right? So this is how that is the reason why I'm saying the magnitude of r vector is x, because it follows the same procedure here, right? This and this will cancel, right? So which means from here we can be able now to calculate or to find the electric field, right? Because we know all the quantities now. We know everything from here, right? So how do we find the electric field then? So the electric field, right? From definition, the electric field, we can simply say the electric field is defined to be, let me use the different color. Okay, I want to use black. So the electric field, which is a vector quantity, is defined to be 1 over 4 pi epsilon 0, right? The integral, right? So how do we find the lower bound and the upper bound of this integral, right? So now you want to find the strength of an electric field at this origin here, right? Or at this point charge here, right? Which is placed at 0 map 0, right? So now due to what? Due to the entire rod, which means we need to consider the electric strength starting from this position of the rod, right? So let me use a different color. Starting from this position of this rod to this position of this rod, which means we need to add all the small charges that we can find in the surface of this rod and test the electric field strength as we move away from the origin. All right, so what does that mean? It means that our lower bound will be what? Will be A, right? Why? Why we have our lower bound to be A? We have our lower bound to be A because we are testing the electric field strength at the tip, right? So we're starting from this position here, which means what is the distance from this test charge to this position? The test charge from the test charge to this position is A, right? It's A. right? So that is our lower bound, right? So what about the upper bound, which means the position or the distance between the test charge and the tip or the last tip of this rod we are referring to, which means that is gonna be, it's A plus L, you see, because this L is the length of this rod, plus A. Why plus A? Because this rod is placed A meters or 8 centimeters away from this test charge, right? So that's why here we'll have F L plus A or A plus L. It's the same thing, right? So which means this is our lower bound and this is our upper bound, right? So what about dq? dq is lambda, it's lambda dx. dq is lambda dx. What about x? R squared? R squared is x squared, right? This unit vector here, r unit vector, is I, which makes sense because this rod is placed along the x-axis, right? So how do we solve this? Solving this is very easy. What we need to do now, we need to say, okay, the electric field here, which is a vector quantity, we take this out of the integral because it's constant, which means we have 4 pi epsilon 0 a L plus A, right, dx over x squared, right? So which means we also need to take that unit vector out of this integral, right? So now how do we solve this? What is an integral of 1 over x squared? That one is very easy. So which means we need to rewrite this equation to say it's like this, right? So what is the integral of 1 over x squared? So it's 1 over x, right? Then it's L plus A. It's A of A to L plus A. So we need to be very careful in writing this. So now you see, now we don't have the integral sign because we already taken the integral. All right, so what is happening here? Which means the electric field can be written as lambda 4 pi epsilon 0, right? So what is there? We need to insert the upper bound, which means it's negative 1 over L plus A minus minus. So it's minus minus, which is plus 1 over A, right? So now, which means we can rearrange this equation to find the electric field to be lambda over 4 pi epsilon 0, right? 1 over A. We're missing something here. We're missing I, right? 1 over A minus 1 over L plus A, right? Times I, right? So this is similar to have what? To have when you solve for this, when you solve this for this equation, what you have something like this. We have Q over 4 pi epsilon 0, right? A L plus A, right? So I was just showing you exactly the final answer, what is happening here. Didn't show you all the steps on how to solve this, but solving this is very easy because from here you need to find the LCD, which is the lowest common denominator, which is 8 times L. Maybe I can do it here so that you can see what is happening. So we have 1 over A minus L plus A, all right? So from here, what you have, we have A, L plus A. So cancel this and this, which means we have L plus A minus this and that minus A, right? So which means from here we have L times A, L plus A, right? You see, times lambda 4 pi epsilon 0, right? Which is this quantity here. So what is lambda times L? You remember from this definition here, which is the total charge of this rod, right? It can be defined as what? As a linear charge density, right? So what is that? So the entire thing here become Q because it's L times lambda, which is Q. So that's why at the end of the day, we have this answer to be Q over 4 pi epsilon 0 A L plus A, right? So this is mathematics, right? You should just know how to do this, right? So this is how you do it, right? So let us take another example. Let us take a situation whereby now it's the same linear, it's the same problem, right? But now instead of putting this test charge here at the origin, we decided to put this test charge where? Maybe here, maybe here, right? So now let us consider doing that. Let us consider doing that example. So it is example 1, right? So on example number 2, what we will do, we will place a test charge maybe somewhere here and move this rod along this x-axis, right? So that we can have symmetry. But now I'll show you in a moment what do I mean by that. All right, so let me clear this. Where is clear? Okay, clear all drawings. Right, so now we know how to calculate the electric field strength when the test charge is placed or is placed along 0 map 0 along the x-axis. Right, so now let's consider this example again. This similar problem, which is example number 2. We have the situation whereby we have this rod again. All right, so we have this rod. This is our rod. Remember, our rod of length L. All right, we have this rod of length L. But then in this situation, this rod is placed in a manner that we have what? We have something like this, okay? We have is placed like this, which means we'll have we have the Cartesian plane here along the y-axis here, and we have the Cartesian plane here along the x-axis, right? So instead of putting the test charge like as we did on our first example, in this case we're deciding to put the test charge along the z-axis, right? Let's say it is the z-axis, right? Along the z-axis, which means we are placing our test charge here along the z-axis at point P, right? So let us define our Cartesian plane again. So our Cartesian plane can be defined by saying that here we will have what? This is along the z-axis and this is along the x-axis, right? Remember, here we have what? We have infinite number of positive charges, right? Infinite number of positive charges, right? So now the question that we need to answer in this problem is that how do you find the electric field strength at this point here, which is point P, right? So we need to answer that question. So here it is the origin. So which means we placed this rod in a manner that we have similar. There's symmetry. Actually, there's symmetry, right? So how do we calculate the electric field strength at point P? Right. So what is the first thing that we need to do? Again, we need to write a definition of an electric field so that we can see what quantities we have and what quantities we don't have. Right. So the electric field here, right, is defined to be 1 over 4 pi epsilon 0. So this is the line, right? Because the charges are distributed, right, on a straight line segment of length L. All right, so the length of this rod is L. We have L here. So it's the length of this rod. Length of this rod, right? So what else is missing? We're missing dq over r squared, right? dq over r squared times what? Times the unit vector r. Times the unit vector r. So this is from definition. So this is from definition. All right, from this definition, all right, what is dq? All right, remember I said for dq, right? So which means, see, when we have continuous charge distribution, which means we need to select a specific region, right? We need to select a specific region. For instance, in this case, we can simply select this region, right? From here, you can say, okay, this is our dx, because we're selecting a small segment along the x-axis, which means if we can zoom this, we can simply say we're selecting this dx, right? So we are zooming that portion of the rod. So this is our dx, right? So this is our dx, which means we are selecting the small segment, right? So this small segment that you are selecting consists of what? Consists of small segment of charges again, right? Which means the concentration of charges in the selected region can be calculated using the linear charge density, right? Because these charges are linearly distributed along this rod, which means dq can be calculated using this formula here, which is lambda times dx again in this situation, right? It's lambda times dx, right? So we can simply say, okay, which means as we select this region here, this region is x meter away from the origin, right? So this is the origin, so which means this is x meter away from the origin, right? That one is very important, right? Why this is very important, right? Because we need to determine even this side, right? So we are doing it like this, so we need to determine it like this, right? So this is r, so this is r in this definition. This is r. Why this is r? This is the distance between this dq, right? So if we say this is our dq, so which means there's a distance between dq and this q here, which is our test charge q0, right? So and we're being told that this test charge is placed at point p, which is in z axis, or we can simply say is z above the midpoint of a straight line. So this is z above the midpoint of a straight line. All right. So which means if this is a right angle triangle, which means we can be able to find the distance between dq and q. How can we do it? So in that particular case, which means we need to use the Pythagoras theorem, right? Which means our r in this particular case, right? So let's say our r squared will be x squared plus y squared, right? So that one is very important, which means from here, do we have everything we need? We have probably everything we need. We have dq and we have r squared. So what is this r squared? Okay, so the distance between the selected region and the test charge. So this r is more like we have the distinct charges, we have positive charge here, and you have positive charge here, and the distance that separates these two, right? It's r, right? So it's r. So even in this situation, you can just imagine this dq and q to be more similarly to the district charges, right? Which means here we have our r, right? So what is missing again from this diagram? We are missing something which is very important, right? So what is that? You remember on the previous example I said, in order to get this thing correct or to get the calculations correct, so you must be able to draw this vector quantity indicating what? Indicating the electric field due to what? Due to that small region here, right? So which means here we'll have DE1 as a unit vector, right? Why I'm saying this is DE1, it's because even on this side of this diagram, we'll have another line here, right? If you select another line here, right? Which means we can be able to find another vector here, right? Which is it's the E2 vector, right? So which means we're selecting another region, right? Due to symmetry, you remember we said that this is placed the midpoint above this rod, which means what is happening here is similar to what is happening this side. So if you can put a mirror here, right, whatever each is happening on the left hand side can reflect again to what is happening on your right hand side, right? So in that particular case, we can simply say here we have our angle theta, right? Why we have this angle theta here? We have this angle theta here because electric field is a vector quantity. So if the electric field is a vector quantity, which means we need to include both magnitude and direction. We need to include both magnitude and direction. All right. So let me zoom these components here. Let me zoom these components here so that you can see what is happening, right? So we can simply draw this as a components, right? So in this case, we have electric field DE1, right? So since this is in two dimension, right? This is along the z-axis and this is along the x-axis. So what does that mean? It means we will have the electric field along the x-axis, all right? So we have the electric field along the x-axis pointing on the positive x values, and we'll also have the electric field along the y-axis, I mean the z-axis, which is E1. It's E1 Z, what is this? So unit vector K corresponding to z-axis. Right. What about this electric field here? What about DE2? DE2. So which means for that one, we will have the electric field, right, which is DE2, right, as a vector quantity, right, in that particular case, which means for even for this one, we'll have the electric field along the x-axis also, which is E. Okay, I think the color here is not good. Let me use black. All right, so here I was saying we'll have what? We'll have DE2 vector, right? Because even for this one, it's a vector quantity, right? So along the x-axis, we'll have what? We'll have E2x, but now we'll have negative I, right? Because this is moving in that direction along the negative values of x. This is moving along the positive values of x. And what about here? And here, let me go back to this color so that you can see. All right, which means along here we'll have this vector here along the x-axis, right, which is they're pointing in the same direction with this one, which means even here we'll have E2Z, right, K unit vector, right, which is very easy. All right, so this one is very important, right, which means the electric field strength here will be due to what? Will be due to this half of this rod moving from here to here and moving from here to here, right? You see from here, you see from this diagram here, from this electric field diagram, you see the total electric field at this point will be due to the sum of an electric field to this side and this side of this rod, right? So how do we go? How do we move from these calculations then? Because at the end of the day, we need to use this definition, right? So we can simply say the electric field at point P, right? Because we defined that point to be point P. At point P is due to what? Is due to electric field 1, right, of the selected region, plus an electric field 2, right, due to that region, because this is symmetrical. Right. So what is E1? Edit E1. How do we find E1? E1 is this one. Is this side. Right. E1 is this side. So which means the electric field at point P is equal to what is E1 again? So how many components do we have in E1? We have two components along the x-axis and along the z-axis, which means from here we'll have what? We'll have E1 xi, right, which is this component, plus y plus, because this is going to the positive values of y, of z, sorry, plus e2 e2z k, and this k is a unit vector, right? Plus, what about e2? E2 will have e2xi, right? But remember, this e2xi is facing in that direction, opposing E1, which means here we'll have negative value, all right? So what about the Z, which means here we'll have plus E2 ZK, E2 ZK, right? So let us continue, which means as we solve this, we have the electric field at point P to be equal to this and this will cancel each other, right? Because you see, this is negative and that is positive, which means the sum or the electric strand at point P will be due to which components? Will be due to these two components, which is E1Z K plus E2Z K, right? So how do we move from here? So moving from here, it's very easy, right? So how do we find how do we solve this equation from here? All right. So it's very easy. All right. So because we need to incorporate even the cos and the sine. All right. So along the k or along the z-axis, right? So we need to have a specific angle because we determine or define our angle to be angle theta. All right. So how do we do it? So if you can simply, let me use the blue color. If we can simply extrapolate this line here so that you can see how to get this angle, right? Which means we have the angle theta here, right? So if we have an angle theta here, which means even here we'll have our angle theta, right? It's very easy. So I'm just zooming this diagram so that I can be able to extrapolate the components, which means here we can simply write this electric field at point P by saying, okay, the electric field at point P is what? It's E1, it's E1 cos theta, all right? Along this vector here, because it's adjacent of hypotenuse, we have E1 already, right? But then what is E1Z, right? But for simplicity, let us say here we don't have D, but instead we have E, so that you don't get confused. So we have E1 here. We have E1, right? So I want you to see where do we get this E1, which is the magnitude of an electric field along the z-axis times the direction of that electric field along the z-axis, which is in cos theta along, okay, right? Plus E2 cos theta along, okay, right? So how do we move? How do we find this? How do we find this? So it's very easy again. So we can simply say this is our equation 1. Right. So let me remove this. Do I need to remove this diagram? Okay, let me remove here so that we can have enough space to continue with our calculations. All right. So using equation number one, which is this one, which means we can find the electric field at point P. So the electric field at point P is equal to what? So how do we find it? So what is the magnitude? How do we calculate the magnitude of an electric field? It's very easy. So the magnitude of an electric field is 1 over 4 pi epsilon 0, right? Times the integral dq, right? Remember dq, but in this case we said dq is what? It's lambda, it's lambda dx, right? It's lambda dx. It's lambda dx. You remember dq, we said dq is lambda dx because we're selecting a small segment, right? If you remember correctly, we said in that case we have lambda dx over, right? Over what? Over r squared, right? Let us put r squared for now, right? Times cos theta k, right? Plus lambda dx again, because this is E2 and this E2, we said this is like a mirror, which means if you have x here, even this side, we have x. So we're selecting the region of, say, the same distance. So even here we have r squared. All right, okay. So it's 1 over 4 pi. So let me put a square bracket, right? Lambda kr squared. So what do we have here? We have cos theta along the k unit vector. Right. How do we solve this? So how do we move? So we can simply say this is equal to what? So this is equal to 1 over 4 pi epsilon 0, right? Epsilon 0 times times what? Right. So let us consider the upper bound and the lower bound of the integral. All right. So to move from here, right, we are moving from the origin, right? So this is the lower bound. We are moving to the origin to the end or to the tip of what? To the tip of this side of this rod, which means we are moving from 0 to L over 2 because we are moving from half of this rod. So here we'll have L over 2, even for this situation here, right? Because we need to have the integral here. We're moving from 0 to the other end of this rod, which is 0 to L over 2, right? Which is very easy, which means we can simply say, when you simplify this, we have 0 to L over 2, right? What is happening here? With times 2 lambda dx over r squared cos theta k, right? Interesting. All right. So how do we move? Right. So let us erase this so that we can have enough space. All right. All right. So now from this equation you can say, okay, let us pause. Let's say this is equation 2. Remember, we said our r squared is this x squared plus y squared. Right. Okay, I made a mistake and this is not supposed to be y squared because we defined this to be along the z-axis and we said the distance here is z. So this is x squared plus z squared. Right. So now what about this cos theta? This cos theta can be defined like this, which means cos theta is equal to what? Cos theta is adjacent over hypotenuse, which is z over r, which is adjacent over hypotenuse. So this is z over r, which is z over the square root of z squared plus x squared, right? Because this r is the distance from the dq to this point here, which is point P. Right. So using equation number 2, what is happening? So we can simply use the equation number 2. We can say, okay, using equation number 2, therefore, the electric fields, the strand at point P can be defined to be 1 over 4 pi epsilon 0 from 0 to L over 2, right? Times 2 lambda dx over what is r? We already know what is r squared. Actually, r squared is x squared plus z squared, right? Times, right? Times cos theta. So what is cos theta? Cos theta is z over z squared plus x squared raised by 1 over 2 times unit vector k, right? Indicating that the electric field is along or it's pointing along the z-axis, right? So now let us simplify this. How do we simplify this? So we say the electric field at point P is equal to what? Is equal to 1 over 4 pi epsilon 0, all right? From 0 to L over 2, right? Times 2 lambda z, all right, divided by let's say divided by z squared plus x squared raised by 3 over 2 dx unit vector k, because it's 1 plus 1 over 2, which is 3 over 2. All right, so we are almost there. We're almost there. All right, which means from here, we can simply say, okay, our calculations can continue from here. All right, which means the electric field at point P is, all right, so what is happening here? So here you can simply take the integral here, right? All right, from mathematics, you can use the mathematics to take the integral here. So as you take the integral here, what do you have? You have 2 lambda z over 4 pi epsilon 0 times x over z squared plus x squared raised by 1 over 2. So when you take the integral of this quantity, this is what you will have. So from 0 to L over 2 at this unit vector k. All right, so now we need another space. So let's get rid of this so that we can have another space to continue. So we need to clear this. All right, so which means let's continue our integral in that side, which means when we apply the lower and the upper bound, which means the electric field at point P can be calculated, right, as 1 over 4 pi epsilon 0, right, lambda L, right, divided by Z, right, times Z squared plus L squared over 4 times this unit vector k. So how do we get this answer? You can simply get this answer by taking the integral here, right? So we can simply take the integral, which is very easy to do. All right, so one may ask, how do we find this L? Right, finding this L is very easy. Or how do we obtain this L and that L from this upper bound? So what you need to do, we need to apply the upper bound, right? So we'll have L over 2 instead of x, right? Because we take the integral respect to x. So that one is very important. We're taking the integral respect to x, right? So when you do those calculations at the end, this is what you will get. So it's very easy. So the recipe here is to understand the equation, to understand all the quantities or all the parameters from this equation and how to obtain those parameters, how to find dq, how to find r squared, how to find this r unit vector, right? So which means you can extrapolate the components, right? Simple. So from knowing the components, it's very easy. You can just go move along with the calculations. You can see from each step that what is required from you. Then you can simply use the diagram, right, to be able to find exactly what is required from you. All right. I hope that is clear. All right.